Hi, welcome to the second lecture of Math 336. Today we'll be talking about section 1.1, which is on differential equations and mathematical models. Okay, so let's begin. Okay, so here we are. So the story that I'd like to tell you today about differential equations is sort of a story about going in two different directions. So we'll start off with the easy direction, which is starting with a function, we can show that it satisfies some kind of a differential equation, which is an equation which involves derivatives of this function. So we'll see that actually showing a function satisfies a differential equation or is a solution of a differential equation is easy. So let's start with this first example. So example number 1. This is actually exercise 5 from the 1.1 problems. So how do we show that this function y of x, so this is y is the dependent variable and x is the independent variable. So y is a function of x. So as when we change the value of x, it changes the value of y. So y is a function of x. So let's look at how we can show that it satisfies this differential equation on the right-hand side. So first of all, let's take the derivative of y with respect to x. So I'll represent that with y prime. So the derivative of e to the x with respect to x is just going to be e to the x. And the derivative of e to the negative x, in this case, we'll have to use the chain rule. So it's going to be the derivative of e, it'll be e to the negative x. And then we have to multiply by the derivative of the inside function. So the derivative of negative x. And what is the derivative of negative x? It is -1. So we end up getting e to the x plus e to the negative x. Okay, so now let's have a look at y prime minus y, and let's see what that equals. So y prime minus y, so y prime is e to the x plus e to the negative x. So that's y prime. And then we'll subtract y, which is e to the x minus e to the negative x. And we see that we have this e to the x cancels this e to the x. And we get 2 e to the negative x. So we have an e to the negative x there, and then minus minus is a plus, so plus another e to the negative x, we get e to the negative 2x. And that allows us to conclude that y equals ex. So I guess from this we can conclude that we get y prime is equal to y plus 2e to the negative x, which is the differential equation we have up there. So therefore y equals e to the x minus e to the negative x is a solution of the differential equation y prime equals y plus 2e to the negative x. So that's how we show that a function satisfies a differential equation, or we'll say it is a solution of the differential equation. Okay, that was a pretty simple example. If you remember the derivative of e to the x, and if you remember chain rule, this is a pretty straightforward thing to check. Let's do another example that's maybe a little bit more involved. It involves the first derivative and the second derivative, and it is actually, we're going to show that two different functions here are both solutions or satisfy this differential equation. So actually, I'm just going to delete that. That'll be fine. So let's delete that. So we have these two functions. Let's start with the first one. So y1 is e to the negative 2x. So let's take the derivative of that, and we will get e to the negative 2x. And then again, we have to multiply by the derivative of the inside function. So the derivative of negative 2x with respect to x is negative 2. And so we end up getting negative 2 e to the negative 2x. Okay, so that's the first derivative. The second derivative is going to be, so we're going to take the derivative of y prime now. So it'll be the constant times the derivative of e to the negative 2x. So that will be e to the negative 2x. And then again, we use chain rule. So we have to multiply by the derivative of the inside function. And the derivative of negative 2x is negative 2. And this ends up giving us 4. So negative 2 times negative 2 is 4. So we get 4e negative 2x. Okay, so there we have all the derivatives we need. So now let's check. So we have y1 double prime plus 4y1 prime plus 4y. Okay, let's see what we get. Oh, 4y1. So I'm plugging y1 into this differential equation. So what do we get? So y1 double prime, that is 4e to the negative 2x. And then we're going to do 4 times y1 prime, which is negative 2e to the negative 2x. And then we will add 4 times y1. So 4 times y1. What is y1? Okay, so it is e to the negative 2x. Okay, so let's make a little bit more space here. I'm just going to add a page right there. Okay. So we added a page. So let's continue this calculation. So what do we get now? So let me just do the following so it looks nice on the PDF of the notes. So this implies that this is going to be equal to, okay, so now what do we have here? So it looks like we have 4e to the negative 2x, and we have another, so here's a 4e to the negative 2x, and we have another 4e to the negative 2x. So in total, that will give us 8. So let's write 8e to the negative 2x. So that takes care of those guys. And then over here, we have 4 times negative 2 e to the negative 2x. So that'll give us a negative 8 e to the negative 2x. And we get that that is equal to 0. So that means that y1 is indeed a solution to this differential equation. So let's write that down. So therefore, y1, which is e to the negative 2x, is a solution of the differential equation y double prime plus 4y prime plus 4y equals 0. Okay, so there we have this function satisfies this differential equation, and so we say that it is a solution of this differential equation. Why did that period come back? I do not know. Let me try to erase that again. There we go. Okay, perfect. So that is what we get. Huh. Now the video is showing me something strange. I don't know why we have these extra words appearing there. That is less than ideal. Let me see if I can do something about that. One second. Let me just pause this quickly, and I'll be right back. Okay, I'm back. I seem to have solved that problem. So I'm not going to insert pages into the document anymore when I'm recording. It seemed to cause a problem. Okay, so hopefully that's okay. The PDF should still look fine, and hopefully it makes sense. All right, so that is the first function. Now let's look at the second function. So it's the same as y1, it just has a multiplying by x there. Okay, so now y2, so I'll say now let's look at this function, y2 equals e to the negative x times e to the negative 2x. Okay, so again, we will start taking derivatives. So the first derivative is going, so now we have to use the product rule. So the product rule says we're going to take the derivative of the first function and then multiply that by the second function. So I'll start there. So the derivative of the first function is, so the derivative of x is the first function. The derivative of x is 1, and that's multiplied times the second function. And then we will add that with the first function times the derivative of the second function. And the derivative of the second function is, it is going to be e to the negative 2x, and then we multiply by the derivative of the inside function, which is negative 2. And let's simplify this. So we end up getting e to the negative 2x minus 2x e to the negative 2x. Okay, so there's the derivative of the first function. And now, sorry, that's the derivative of y2. And now the second derivative of y2 is the following. So we're going to start with the first term. So the derivative of e to the negative 2x, it's e to the negative 2 times the derivative of negative 2x, which is negative 2. And now we're going to subtract 2 times, and now we're going to do a product rule of the x times e to the negative 2x. So again, we'll take the derivative of the first function times the second function, and then we will add to that the first function times, let me just move, I feel like I'm running out of space here, so let me just move that down there like that. And so the derivative of, so we have x, and then times the derivative of e to the negative 2x. So that is going to be e to the negative 2 times the derivative of negative 2x, which is negative 2. And we have that. So, okay, so let's simplify this. So what the first term becomes negative 2 e to the negative 2x. And then we'll have negative 2 times e to the negative 2x, and then minus 2x e to the negative 2x. Let's see, can this be simplified further? Yeah, I think so. it looks like we have two e to the negative 2x terms. We have one here and we have another one here. So let's combine those together. So we have a total of negative 4 e to the negative 2x. And then we'll have, if we distribute this 2, negative 2 times negative 2 gives us plus 4x e to the negative 2x. Okay, so there's our two derivatives. So maybe I'll just highlight these right here. So there's our first derivative and our second derivative right here. Okay, just so we see where they are. Okay, so there's our first derivative and our second derivative. And now let's plug those into our differential equation. So therefore, what do we have? So our differential equation is y double prime plus y4 prime plus 4y. So y2 double prime plus 4y2 prime plus 4y2. Okay, so we're going to plug it into that differential equation and we'll see if we get 0. So this first term, y2 double prime, that is going to be negative 4 e to the negative 2x plus 4x e to the negative 2x. So that is y2 double prime. And then we will add to that 4 times y2 prime. And let me just go like this. I'll just copy that and I will paste it right in there. And I will remove that red. Okay, so that is y2 prime. And then we need to do plus 4 times y2, which is x times e to the negative 2x. That one I remembered. So that is what that is. Okay. So we simplify this. Let's see. So this is quite a mess. Let's see if I can make any sense of this. So I'm looking at the e to the negative 2x terms, and I see there's negative 4 there. There's another plus 4, so those guys will cancel. And I think that's it. So let me just mark that up in red. So this guy here is going to cancel this guy here. Once I multiply that 4 in, those will cancel out. And then we also have, for the x e to the negative 2x, we have 4 of them here. Then we have negative 8 of them. So once I multiply this 4 times this negative 2, we'll get negative 8. So that'll be negative 8. And then we have another 4 of them here. So we'll have 4 plus negative 8 plus 4. And again, those will all cancel out. So this will cancel with this and this. And in the end, everything cancels and we're just left with 0 as we expected. Okay, so that means that y2 is also a solution of this differential equation. So let's write that down. This time I will just grab this stuff and I will scooch it down like that to make room instead of adding a page, because that seems to cause the recording to get confused. So what do we have now? So therefore, y2, which is equal to x e to the negative 2x, is also a solution of the differential equation for, oh no, it's not 4. It was y double prime plus 4y prime plus 4y equals 0. Okay, so this is a solution So this function is a solution of this differential equation. There we go. I'm just going to move that down a little bit away from that page break right there. Okay. So this differential equation we found actually has two different solutions to it. So, that is already telling us something interesting, that just like polynomial equations, for example, can have different solutions. You can have two solutions to a polynomial, to a quadratic equation, for example. You know, the quadratic formula has a plus minus in it, so it gives you two different solutions. So the same is true for differential equations. You can have actually more than one solution to a differential equation. Okay, so let's continue our discussion here. I'm just gonna move this stuff back up to just below here. All right. So that's how we can take a function and show that it actually satisfies a differential equation. So that's the easy direction. Going the opposite direction, which is often referred to as an inverse problem, of finding the solutions of a differential equation is not as straightforward. So if you're given a differential equation and you're asked to do the opposite thing, which is to find the solutions, so go from the equation to the solutions rather than from the solution to the equation. So going from the differential equation to the solutions, this is not as straightforward. So the forward direction was simply just some calculus, take some derivatives, do some algebra, not a big deal. The inverse problem will be more involved, and that is the purpose of this class, is to learn how to go from a differential equation and obtain a solution. So this more difficult, what's called an inverse problem. A lot of inverse problems in mathematics, and usually they're all of this form. Going the forward direction is easy, going backward is not as straightforward. However, in some cases, a good technique to find a solution to a differential equation is to guess the form of the solution. So here's an example of that. So now we're given this differential equation 4y double prime equals y, and we'd like to find the solutions of this, you know, maybe one or possibly more than one solutions of this differential equation. And the technique we'll use here is we'll just make an educated guess that, you know, perhaps this is some kind of an exponential function, but so it'll be like e to the rx, but we're just not sure what r is. So let's see if we can determine the values of r, which will satisfy this equation. Okay, so to do that, we will start with y equals e to the rx, and we will take its derivative. So y prime, so this will be the derivative of e to the rx is the derivative of the outside function, which is that, and then times the derivative of the inside function. The derivative of r times x with respect to x is r. So we will get r e to the rx. Okay, so that's the first derivative. And then we do need the second derivative as well. So this will be r times, and then we have the derivative of the outside function, and then times the derivative of the inside function. The derivative of r times x with respect to x is r. So in total, we get r squared e to the rx. So that's the second derivative. Okay, let's plug these guys into the differential equation. So we have 4 y double prime equals y. So let's plug those in. So we'll have 4. So y double prime is r squared e to the rx. And then y is just e. Oh, it became a circle. I don't want a circle. I would rather have an e. So e to the rx. Okay. So let's just write this out. I'm just gonna delete these parentheses. That makes it a little bit nicer, because what I'm looking at now is we have this equation, and we have this common thing on both sides. We have e to the rx on both sides, right? So there's e to the rx there, and there's e to the rx there as well. So let's divide both sides of this equation by e to the rx. E to the rx is always going to be non-zero, so we don't have to worry about it being 0. We know exponentials, or e to the anything, is going to be something positive, right? So e to the rx is guaranteed to be non-zero, so we can definitely divide by this. So let's divide this equation on both sides by e to the rx, and I will represent that by just saying I'm going to, well, yeah, so I'm just going to, this cancels with that. I'm just going to divide both sides by e to the rx. And what am I left with? I am left with 4r squared equals 1. Oh, okay, so this is an algebraic equation now for r. I think we can solve this equation for r. What's a good way to do this? Let's divide both sides by 4 and then take the square root. And I think it's not too hard to see. I'm just going to squeeze this in here, that r is going to be plus or minus 1/2. I think that is the solution. So maybe let me just remove this box. I'd rather emphasize this. There's our solution right there. So we actually do get 2 different values for r as possible solutions. So with those values of r, that e to the rx will be a solution of that differential equation. Okay, let me just make a little bit more room so I can draw a conclusion. So let's just move this down a little bit like that, a little bit more. Okay, that should give us enough room right there. Okay, perfect. So what does this mean? So therefore, we will have, let's call it y1 equals e to the 1/2 x, and y2, so these are 2 different solutions, e to the negative 1/2 x are both solutions of the differential equation for y double prime equals y. Okay, so we ended up getting, so there's our differential equation right there. So we ended up getting 2 solutions. Just like we saw before, we can have 2 solutions to the same equation, not a big deal. And I think that is the goal. That is what we wanted to do. So we solved this differential equation in that we found 2 different solutions to this differential equation. However, the story becomes more interesting now. So let's make the following observation. So in this previous example, we found these 2 solutions. However, we can actually get even more than just 2 solutions to the differential equation. We can actually take that that second solution, that e to the negative 1/2 x, and we can actually take that, so that's y2 right there. We can take that and we can multiply it by a number, say 2. And if you go through the calculation, you can easily check that this is also going to satisfy this differential equation. It's not too hard to see. We can multiply that function by negative 10, and that will give us another solution. Sorry, negative 1/10. That'll give us another solution. We can multiply it by 100, and this will give us yet another solution. In fact, we can multiply this function by any constant number we want, fraction, irrational, any constant number, and it'll still give us a solution to the differential equation. So yeah, any function of the form y equals c e to the negative x/2, where c is just a constant number. This is a solution, and the same is true for that, for the function e to the x/2, which we saw was a solution of this differential equation. We can also multiply that by any constant number, and that will also be a solution. So now we have a lot of possible solutions, and moreover, we can actually take any of those two general form of solutions, we can add them together, and this also will be a solution of the differential equation. And in this way, we can actually obtain what's known as the general form of the differential equation. So what is sort of all possible solutions of this differential equation look like? They all look like exactly this. So it'll be I guess we call this, we call that y2. So so we can just take any constant times this function, e to the negative x/2, and we can add any constant, any other constant, doesn't have to be the same constant, times e to the x/2. And it's quite easy to check. This will satisfy this differential equation. And in fact, every solution of this differential equation is of this form. That's why we call this the general form of the solution of this differential equation. So this is interesting now. What are we going to do about these constants? So, you know, these constants are actually, you know, they're unknown, right? Like we don't know what these things are. These are unknown constants. However, how can we determine these unknown constants? To do that, we need additional information. And this is usually like initial position and initial velocity, right? So if you give an initial position and velocity, then that will determine the rest of the motion of this object according to this differential equation. Okay, so let's see an example of how we can determine such a constant. So let's look at first this function here. So we have this function y of x equals c x to the negative x plus x minus 1. And we'll show that it satisfies this differential equation, y prime equals x minus y. Okay, and then after we've made sure that, you know, we believe this is a solution, then we'll use some additional information to determine the constant c. And what we'll use is the initial position, for example. So it's a sort of like what is the value of y when x is 0. And so this initial condition is going to be y of 0 is 3. And using this, we'll be able to determine the constant c. And that'll give us a unique solution to the differential equation that satisfies this initial condition. Okay, so let's do this. So first of all, we want to take that function y of x equals c e to the negative x, and I forgot already, is plus x minus 1. Okay, so plus x minus 1. Okay, so let's take the the differential equation we're interested in is that one right there, x minus y. Yeah, okay, so let's show that this is a solution. So y prime is going to be, and this y of x is just saying that, you know, y is a function of x, which sometimes we write, sometimes we don't. So I'm just going to not write it in this case. Well, I mean, we could, but anyway. So let's take the derivative of this. So it'll be c times the derivative of e to the negative x. So we take the derivative of the outside function, and then we have to multiply by the derivative of the inside function. And the derivative of negative x with respect to x is negative 1. Now, plus the derivative of x. This is going to be 1. And minus the derivative of 1, and that is 0. Okay, so what does this become? We get negative c e to the negative x plus 1. Okay, all right, so let's check. So let's do y prime plus y. And we want to get x, so that should give us x. So let's plug this stuff in. So y prime is going to be negative c e to the negative x plus 1, and then plus y, which is c e to the negative x plus x minus 1. Yeah, this is working out. Okay, so we have a negative c to the negative x, negative c times e to the negative x, and we have a plus c times e to the negative x. So these two will cancel, they add together to 0. We have a plus 1 and we have a minus 1, so those cancel. And we're just left with x. So that is equal to x. Okay, so that is enough to verify that that is a solution. Let me just make some more room here. Just move that down there. Okay. So therefore, y of x equals c e to the negative x plus x minus 1 is a solution of the differential equation y prime equals x minus y. Okay, so now we want to determine what is the value of this c. So our initial condition is y of 0 equals 3. Okay, so what is y of 0? So let's start with y of 0 equals 3, and y of 0, so I'm just going to plug 0 into this function, so I get c times e to the negative 0 plus 0 and then minus 1, and that, according to this initial condition, should be 3. So we get c times e to the negative 0. Well, that's e to the 0, and e to the 0 is 1. Any positive number, or any number to the power 0 is 1. So we'll get c times 1. So that's what that first thing is. And then plus 0 minus 1. So we get minus 1. That equals 3. So if we solve this for c, we end up getting c is equal to 4. Okay, so c is 4. Let's put a box around. So c is equal to 4. So we determine the constant that satisfies that initial condition. And so therefore, the solution is that satisfies the differential equation and the initial condition is 4 e to the negative x, I believe, yeah, e to the negative x plus x and then minus 1. So is the solution of the differential equation y prime equals x minus y, satisfying the initial condition that y of 0 should be 3. All right. Okay, so we did it. We were able to get the solution of the differential equation that satisfies our initial condition. So we satisfied this differential equation and we satisfy this initial condition. So this is the function that we're after. Okay, I think at this point, it'd be good to have a look at plotting some of this stuff and see if we can sort of visualize what's going on here. I think it would be helpful. So the algebra is nice, but it's also nice to have a nice picture to look at. So let's go over to Geogebra, which is a free plotting software on the web, and we will use it to plot several typical solutions. So I will be right back with that. 1 second. Okay, and we're back. So here I am in my browser, and I've gone to this website, geogebra.org. So let's go ahead and use this website to plot this. So I'll start the graphing calculator. There we go. And let's start by so the instructions in this exercise say that we should use GeoGebra to plot several typical solutions. So the typical solutions were y equals c times e to the negative x. So I often write that using the exponential function. So it's the exponential of negative x. And then plus x, and then we had minus 1. All right. Okay. So there's a plot. Oh, and it realized that c was some constant, and it gave us a slider. So we can now move this slider around. So right now, c is equal to 1. Let's move this to the value of c that we found, which I believe it was c equals 4. So let's move that over to c equals 4. Right there, and let's check. Yes, okay, so you can see that the y-intercept of this graph is at 3, and that means that y of 0 is equal to 3. So that was the initial condition that we wanted to satisfy. So that's perfect. So, but it's interesting to look at this slider. Let's look at other possible solutions. So these are going to be other solutions that satisfy different initial conditions. So if c was say 2, okay, so when c is 2, y of 0 is going to be 1. So that would be a different initial condition. So if that was the initial condition we wanted, then the c that we get is actually 2. So let's just kind of animate this and see what happens as c changes. We can get a better understanding of what this function is doing. Whoa, okay, so it suddenly flipped at some, I guess that was when c equals 0, we get a straight line. And then sort of, okay, all right. So I see what's going on here. And so let's just pause this for a second. So what's going on here is that when C is positive and X is like very negative, then this term is going to grow like really rapidly. But when X gets large, moves to the right, then this term actually becomes quite small. It's basically 0. And what we end up seeing is a graph of basically X minus 1, which is that straight line part there that we see. And in fact, we can sort of, if we just set C equals 0, there's that straight line, that X minus 1 straight line. But when C is negative, we get a different situation. Suddenly, when C is negative, now this first term is going to become extremely negative very quickly for negative values, very negative values of X. So, but still, as X gets positive, it's still this first term just goes to 0, and we get that straight line appearing right there. Okay, great. So what is a nice way to, let's just go back to our solution, which was 4, I believe, right there. So there's our solution. Maybe we can actually just plot that as another line. So here, what's our solution? It was 4 times the exponential of minus x plus x minus 1. Okay, there's our solution. And now I think I can play both of them. So you can see the green is like the general solution. It changes with C. And then we have our solution that satisfies our initial condition, which is this orange solution. Now, what's really nice about GeoGebra is it allows us to get another way to visualize what's going on with these solutions of this differential equation. We can plot what's called the slope field. And this will give us a little slope mark at each point in this field. So I know that the derivative is x minus y. So if I type slope field of x minus y, this will actually give us a little representation of the slope that this function should conform to as it's moving through the plane. And you can see how indeed this function, as it's moving around, it is following almost like this wind field, or this kind of a vector field, or technically it's a slope field. So it is obeying the slope field. You see this curve is actually has the same slope as these little lines as it's moving around. And so one way to think of what's going on here is we're sort of starting at some point, and then we are just moving through this slope field and making sure to change our direction according to the wind, So that's what's going on. So, and that's a nice way to think of it. We can actually look at solving this differential equation numerically. So there's a function called solve ODE in GeoGebra, which gives us a numerical solution of this ODE. And we need to provide it a list of derivatives, an initial x coordinate, a list of initial y coordinates, and then a final x coordinate. Okay, so let's do the list of derivatives. We use curly brackets for that, curly braces. So we get x minus y, that's our list of derivatives. Our initial x, let's do 0. The initial, we have to give a list of initial y values. Just for, to give us something different than the orange line, let's give it 2 as the initial y value. And then we have to give it like a final y value, or a final x value. So I'll use 6. Yeah, so let's just go to 6. Okay, and already it's given us our numerical solution. Oh, maybe, I wonder if I can change this. Well, that's fine. Let's keep that label. So the black line here is our numerical integral. And let's just zoom in on this a little bit. So how does this numerical integral work? Well, what it does is it's just taking very small steps, and at each step it's looking at the slope field and saying what is the slope of this function here, and it just moves a little bit in a straight line according to the slope field. And it just keeps doing that. At each new step, it just looks at the slope field again and says what is the direction I should be going, and it's gradually adjusts its direction according to the slope field. And it just does that a bunch of times for very small steps, and it gives us this nice curve actually. And I think let's just quickly see if I give it our initial condition of 3. Boom. Yeah. So that just agrees, that lies right on top of our orange line. Of course, it starts from 0 and goes to the right, but we could have started somewhere else as well. We didn't have to start at 0. We could start anywhere. We could stop anywhere. But that looks pretty good. So that's how you get an approximation for your solution. Another thing we can do with GeoGebra is we can actually say solve ODE. And solve ODE is actually going to try to solve this ODE algebraically or symbolically. So it'll be a symbolic solution. So what do we need to provide it? I guess we just need to provide it the, so let's start with this first option and just give it the, this function f prime of y, of xy. So that as we know, it's going to be x minus y. Well, that was interesting there for a second. I got something completely different. X times y gives us that. Okay, so x minus y, and what do we get? Oh, okay, so it actually knows that, well, so it put a 1 there, but it seems to have recognized that this one, oh yeah, that's right. So this one is the C1. So so it knows that this this needs some sort of arbitrary constant here. Let me pause this one. There's too much stuff moving around. So let me just put that up there at 5. Yeah, so it actually solved it. It gives us the general solution. That's pretty cool. And if we were to go in here and then, let's see, how do I edit this now? Okay, so now instead I want to give it like an initial point. So I'll give it the point 0, 3. And let's see what we get. Okay, let me turn off this stuff. Maybe I'll turn off this and turn off that. Okay, right. Yeah, that's it. So it actually, not only did it solve the ODE, but it also determined this coefficient, which is 4. So that's sort of some options that you have for solving ODEs in GeoGebra. You can solve them numerically using nsolve ODE. And we'll talk about that in chapter 6 in detail. And you can also solve them symbolically as well. So that's pretty cool. And it gives us this really nice visualization. So I will, let's see, maybe I won't put all of this into the PDF, but maybe let's plot like this guy and this guy. Yeah, that's probably good. So maybe I can just put that down there or something. Yeah, that looks pretty good. So I'll take a screenshot of this and I will put that into the notes. So we have a record of it there. And that is it. So I will stop there and I will post this video. Thanks for watching.